depending on the type of difference in work function typically is the amount of energy required to take electron out of the material. So if you look at platinum, silver, gold, copper, etc., people have measured this work function and they will go. So depending on what metal you put on what oxide, you can create the so-called property contact, or you can create a point. This is not just only disruption of bonds that you get on the surface that can be in certain states, or in absorption of the gas one that can create the local redistribution of charge, which would be considered a kind of defect in that sense. Or, depending on the type of metal you are putting, you can create this kind of something. What happens is you choose a metal that's a work function larger than Fermi energy level of your oxide. Electron will actually transfer from the oxide to the metal. And that redistribution of charge will create this very lengthy output. So this creates a shock wave. And so if you set a metal with a metal contact, so it's not sampler. And if you measure the electrical conductivity of your sample, obviously you're going to get the electrical conduction that is amounted or associated with the overcoming of the shock wave. So sample is the conductor area resistance. That's what you want to measure. But instead you want to measure the contact potential related resistance. So clearly that's not your sample. So when you are measuring the conductivity of the samples, you don't want Shakti. But people use Shakti contact as a device. So for example, if you create a Shakti contact, and if you now use this and expose it to some gas, like hydrogen or carbon monoxide, or oxidizing gas, and so on. So depending on whether it's reducing or oxidizing gas, it will actually modulate that curve. So because of the Shakti barrier, if you measure the IV of the sample, it will get non-linear IV. Non-linear IV has to do with, in fact, this is not a good drawing. In fact, it shows that up to certain applied voltage, this is supposed to be voltage, there will be zero current because of the Shakti barrier that is created like contact. But for an equivalent amount of voltage out for the current will start. Okay. So what people do is the Shakti barrier use the gas sensor. So depending on what gases absorbs on that contact, it will either make the Shakti barrier larger or it will make the Shakti barrier smaller. So for example, if you absorb reducing gas and then CO, it will actually strengthen or lower the Shakti barrier. So your threshold voltage that you need to apply get zero current to decrease. So meaning that this IV curve will keep on shifting to the left as you increase the resistance. And then shifting the IV can be calibrated gas contact. Well, this is not desired for electrical conductivity measurement. People use this as a device. The defect for electrical conductivity measurement, we want to use metal whose work function is lower, smaller than the Fermi energy. So the band bending would be down. So at the contact, it will be a downhill flow. There is no extra power. And in that case, you will get a oblique behavior, straight line. And from the slope of that IP, you can measure the conductivity of this difference. So for electrical conductivity, rather than given an oblique contact, but for a device, you have one refractive. So that's something, which is, you can get, charge distribution, which would be considered as a localized defect. And the semiconductor content. So either N-type, B-type, or even NM, two different materials will have different permeability. And eventually, when you put the contact, they have to equilibrate. Okay. So there will be global redistribution of charge. Something like this, which will create an inbuilt electrical potential. And then, depending on the bias, you see that depending on which way you apply your bias, either that will diminish or increment that local distance gain from the distribution of charge and semiconductor system, which is also referred to as defect, interfacial defect in semiconductor literature. In ceramic, ionic state charge is a very common thing. Typically, it happens around grain boundaries. So you'll actually see redistribution of charges across the grain boundary that would be a localized potential created because of redistribution of charge, and that's typically referred to as state charge again. And it's typically another. So there are different types of localized defects that can create surfaces, interfaces, grain boundaries, gas molecule absorption, all sorts of reasons we look at surface defects. Here I development soon. I was talking about, and you will see some example of how surface defects will vary as we move into the material from the surface. So again, magnesium oxide, we talked about property, which is creation of, you take a magnesium and a magnesium site, put it on the surface of the material, meaning you're basically yanking out the magnesium and creating a vacancy on the magnesium site. Similarly, you can look at creation of oxygen vacancy. Remember, Schott's effect was creation of cation and anion. And again, looking at, so this is your step number 1, write the equilibrium reaction. This is step number 2, express the equilibrium constant for creating magnesium vacancy. And the reason we are not talking about separate creation of vacancies of magnesium oxygen is each of these may require different amount of energy. And one may be easier to form than the other because of the bonding energy and so on. So this is why it's being treated separately. So the equilibrium constant associated with that reaction is right there. So that's step number 2. And then you can look at the, the energy, the amount of energy you spend creates defect as sum of the 2. So this is the energy to create the magnesium vacancy, this is the energy to create oxygen vacancy, so you just add it up to get you calling that energy for creating some. Now we're going to look at what if those energies are different. Let's say, energy for formation of cation vacancy is less than formation of oxygen vacancy. Then the surface will be enriched in magnesium that you're yanking out of and putting on the surface to create the vacancy. And that will create kind of a charge distribution as we go from the surface inside. So then we can actually look at that as an electrical potential over distance. And because of that, you can look at an electrical potential as you move from the surface to the bulk. You can solve this actually by solving this Poisson situation. You can look at the electrical potential. This is Poisson equation. This is density of surface charge. And then, one of the easiest solutions for one-dimensional scenario. And you will get from the solution of this Poisson equation, you will get actually distribution of vacancies, defects that you are creating as a function of distance. And this will give you, both will involve this amount of energy that you need to spend to create this spectrum. So this is the energy to create cation vacancy, energy to create cation vacancy. It will have some terms that will involve this electrical potential as a function of distance. And these are clear thermodynamics. So it will always have this exponential form with 1 over kT in the denominator. Because it's thermodynamics. You can set some boundary, initial condition and boundary condition. And if you set the electrical potential at infinite distance, meaning well into the bulk, you can actually show that charge times the electrical potential in the bulk will be related to the difference between the particle defect formation. So that's the difference between the cation vacancy versus the ionic. And then if you plot this, this is the vacancy distribution, look at how it varies on the surface. Very high, and keeps on decreasing as you move into the axis, increasing as you move into the bulk. Oxygen vacancy concentration on the surface was very little, because this energy of formation of this defect was smaller than this energy. But eventually, as they move into the bulk, they become equal. Does anyone remember what was the electron neutrality condition for Schottky defect in magnesium oxide? It was that this is exactly equal to that. Therefore, the electron neutrality. You can see that the electron neutrality condition holds in the bulk. So when you were writing that electron neutrality condition, we were referring to the bulk, not the surface. On the surface, you can see that it can vary quite a bit depending on how different the energy is. But eventually, in the bulk, you will come to an equilibrium vacancy concentration of each of these that will equal. You will be an electron neutrality condition of bulk, which does not apply in certain. By the way, this distance is over tens of nanometers. So you're talking about really surface layer defect type scenario. But if you're dealing with a device that involves only the surface of if near surface things, then this is going to play a huge role of the implication of which for bulk defect there will be equal, so there will be no difference in impact on the device performance. But any surface related or nanometer level or few nanometer level functionality, this will improve. If you do this for another example, we talked about that aluminum oxide doped in magnesium oxide. And I don't know whether you remember the electron neutrality condition for this case was this fraction was equal to 2 times that fraction. There was a factor of it. You can see that if you again go through the solution of Poisson equation in this case and look at the distribution of defects. So this is your token substitution distribution of aluminum, magnesium, cytosine away from the surface. And this substitution was related to creation of magnesium vacancies. You can see that they're going to vary near the surface. Eventually, in the bulk, they will fulfill this condition. So there will be some difference that will be represented by this factor. They will not be done. Okay. But again, the main thing is that near surface, these defects are very wide, and that is an indication of surface-related functionality. So people, in surface interface science devices that are made based on surface properties, they are interested in this kind of defects and their impact on the performance. So that brings me to this controlled atmosphere processing of material. You see that I'll show you some data for titanium dioxide, carbon dioxide, and nickel oxide to create some level of non-stoichiometry. And non-stoichiometry was related to creating this kind of solids where we from titanium oxide we go into something like non-stoichiometric TiO2 minus X. So to create precise amount of X, we have to control precise content of PO2. Because the PO2 will actually tell you what the X value is. And you change the PO2, X value will change. So that's your tuning knob. That's what you are tuning to create control. And the type of pressure that we would need to, these are ranges for non-stoichiometry. You can see that huge ranges, and particularly to create 2 minus X, you have to be on the low side of offset socket to increase your X. Okay. And you can see some of the phase stability and their range of PO2 in logarithmic side. Logarithmic PO2 minimum barrier maximum. So this gives you the ranges. There's a negative sign there. So these are going to tend to be negative exponent, I should say. And different material will vary. In fact, sometimes it will go from, it will completely transform into different states. So you can transform your TiO2 and increase that X so much that it will actually transform to TiO2 or Ti2O3. But titanium dioxide, the root ion, may still be stable within some range limits. So even if you increase X to maintain that phase with different levels of noxy. So you can see that we're talking about creating the range of PO2. So the question is, how can we create that in the lab? So one idea is that you can dilute your oxygen by mixing with nitrogen is not going to work too effectively because nitrogen still in we have some oxygen. Even argon has 10 sub-ppm of oxygen. Nitrogen has 11. So, I think you can dilute oxygen by high purity argon. But the best you'll be able to do it 10 to the negative 10 of this. But if you want to go to some values like This is not good. So there has to be other alternative. One alternative, very effective alternative, is mixing two different gases. You can actually mix CO and CO2. Or you can mix H2 and H2O. And you can see that the idea comes from the equilibrium between those two gases involving oxygen. So if you, CO, for example, reacting with half a mole of, people write that, oxygen gas, and the equilibrium will give you CO2. In thermodynamics, it's clear that if you mix CO and CO2 at a particular ratio, at a given temperature, it will create a unique CO2. Same thing with hydrogen and water vapor. Same idea. Hydrogen gas and, the reaction goes in a very similar way. It will give you H2O, water vapor. So a combination of certain ratio of this gas with that gas will create a unique CO2. And by doing this, you can actually create very low output, which is often done in the lab. You have to, take precaution and make sure CO is not big. CO is very, very little. It exceeds beyond certain concentration level, we can kill it. So usually, where this kind of gases are mixed, there will be CO detector mounted in the lab, so that you know when to get out before if there is a leak. Anyway, so this is but the problem with CO2 mixture is the problem highlighted. CO2 mixture is that if you create very low pH, where this CO mixture will be in a range where carbon will actually start depositing onto your sample. So it has its own limit. That if carbon is depositing onto your sample, it will short circuit that. Particularly if it's making connected cathode, because carbon is a very good conductor. Okay? So sometimes, people pay attention to CO2 mixture and it has to go extreme. In that case, hydrogen water vapor that doesn't give you that carbon concentration. So that's the other alternative. The third way that you can do is that you can pack metal oxide. Let's see if I can have studied that time. Right? Yeah. So on the electron diagram, you can actually find out that, for example, if you take combination of Fe and FeO, for a given temperature, you'll be able to create an equilibrium PO2 to keep your iron and iron oxide in equilibrium. So imagine that you take a quartz tube, for example, and vacuum it up. Just create that. And then in that quartz tube, when you pack your mixture of powder, iron and iron oxide, and you seal it, gas-tight seal, and now take it to 1000 degrees Celsius or 800 degrees Celsius. It will create an equivalent PO2 that is given by the equilibrium value that coincides with the value on the bound, because iron and iron oxide. If you can actually determine from element that what that PO2 will be at 1000 degrees C, to keep iron and iron acidic. So in that vacuum chamber where you affect this mixture of powder, actually creates that, it's a little bit difficult experiment because now in that quartz tube, you find, in addition to that sort of Rhine step there. Rhine step, the German scientist. So it will be equivalent CO2. And when you heat up your material will be exposed to that. And that CO2 can be made very, very low, depending on what. You can actually take a mixture of oxide and oxide, something like Fe2O3 and Fe3O4. That will work because there is an equilibrium boundary between Fe2O3 and Fe3O4, and so on. Okay, so there are alternative ways of creating variable. People do this experiment in the lab to create those kind of pressures. You can see some stability diagram that shows. So this two boundaries will determine the level of non-stoichiometry that is created, something like that, Fe3O4. And that's an important parametric method. So by changing the X value, non-stoichiometry, going from this boundary to the other bound, you can create different levels of non-stoichiometry in your magnet. And those non-stoichiometry will decide what is the level of paramagnetic power. So you can actually tune that I want exact magnetic moment of this band simply by fixing your X in a non-stoichiometry. And then, only way you will be able to create that is put that magnetite component of your furnace and control the PO2 exactly at that moment. That will change the paramagnetic property of that. So these are real life. People do this experiment and make this kind of devices. You can look at the same diagram in different form. You can see that this is Fe0, this is Fe3O4, and this is Fe2O3. It's interesting. Iron is a metal, and depending on the oxidation condition, and oxidation condition is controlled by PO2 and temperature. You can make either boostite, which is an insulator, FeO, or hematite, Fe2O3, which is a semiconductor, glass band semiconductor, band gap loaded somewhere between 3 and 4 levels. Or magnetism, which is a very good metallic. So simply by oxidation state of your iron, you're making different reactions that have completely different functional problems. And then on top of that, you can then control the non-stoichiometry to fine-tune your functional problem to a particular level of so that's the control. And the only knob that you're going to time is your losses. You do this at a given temperature and then dial PO2 to create different levels of non-stoichiometry. Same thing with materials like cobalt oxide and nickel oxide and so on. You can see that it's a huge range of non-stoichiometric problems. So all the way from this boundary to that boundary, the material will remain cobalt oxide, same thing, with different levels of, this delta, the same events. That it's cation deficient oxide. But then if you cross this boundary, it will convert into a different cobalt 3 oxygen 4. Completely different phase than cobalt oxide. But you can see that there's a huge range of non-stoichiometric cobalt oxide created and you can tune that delta value. Okay? Yeah, I talked about delta value here, and you can see that. Okay, I already talked about this. I talked about carbon contamination at extreme levels of CO2, CO2. So the alternative is hydrogen water vapor. So how does the linear diagram work? You probably know that. Is that I think this is the silicon dioxide looking at 1000 degrees Celsius. So you draw a vertical line to that equilibrium boundary, and then you can use this reference point O, H, and C to calculate this quantity. So you can use O, calculate PO2. So this is how it's done. So you just use the reference point O, go through that intersecting point for the temperature on the boundary, and read the PO2 value. It looks like the equilibrium PO2 to maintain silicon dioxide at equilibrium at 1000 degrees Celsius is 10 to the negative 28 atmosphere. So what does that mean? That means that if you keep your PO2 content lower than that value, silicon will never oxidize. If you exceed that, silicon will oxidize at that temperature, and it will form silicon dioxide. Or you can turn around and say, if I make a right stack of silicon and silicon dioxide mixture, you can just take powders of silicon and powders of silicon dioxide and mix it mechanically, 2-phase mixture, and pack it in a vacuum chamber and heat it up to 1000 degrees Celsius. It will actually create a PO2 of 10 to the negative 28 mostly. So that's the idea of Einstein. Okay, if you want to get the answer in terms of the other axis, ratio of CO2 or ratio of water vapor, you can do that. So for example, if you are interested in CO2, use this reference point C and do the same exercise. So reference point C, go through that temperature intersecting point and come all the way to CO2 axis. It looks like the ratio of the partial pressure of CO to CO2 could be closer to 10 to the 7. So you have to mix it in a ratio that creates that number. And that will create an equivalent PO2, which will be exactly 10 to the negative. But I told you that the 10 to the negative 28 atmosphere by diluting oxygen is almost impossible. So if you want to create that kind of pressure, don't even think about diluting oxygen. You immediately say, well, you have to mix CO and CO2 of the equivalent PO2. And you can get that answer from the element time, what that mixing ratio should. Or if you are mixing hydrogen water vapor, you can get the answer by using reference point H. And yeah, it's much closer to 10 to 7. Okay. Anyway, so we have to mix the hydrogen and water vapor in a partial pressure ratio that comes up to that will create a PO2 of 10 to the negative 28 atoms. So elegant diagram has answered all of these questions that we use all the time to create this controlled atmosphere in processing of. And people talk about sulfidation of metal. They have created elegant diagrams on metal sulfides, very similar, where the only difference would be one of the potential here would be partial sulfur instead of partial pressure of oxygen. Oxidizing your knob is oxygen. If you're sulfidite in metal, your knob is sulfide. So they talk about similar type of, elegant diagram for metal sulfides. So again, as far as the experiment goes, you need the so-called controlled atmosphere arrangement. So your sample will have to be in an environment that are gas type filled at both ends. This is for high temperature metal. So for high temperature metal, you use ceramic like aluminum, or you may use ordinary. Aluminum is better, more stable. And then you would be probably going to 1500 degrees Celsius. And this ends will be red hot. So for safety reasons, what they do is they put all the stainless steel metal cap gas tank, so there will be pouring. So that it gives, gas tank heat. And then, so that your pouring doesn't melt, you'll be using water. So there's a water cooling system that will keep this stainless steel end cap cold enough, so that your pourings do not deform, because if it falls, it will give leakage. Has to be absolutely gas tight. So this is pouring and would create quartz tube. You're not going very high. So with quartz tube, I think it's safe to go to 900, 950. You don't want to exceed. Even if you're doing it for short amount of time, 1000 degrees is probably okay. But if you want to go beyond 1000 degrees Celsius, you have to use ceramic. Quartz tube is easy to have. You can machine it. You can create, don't have the detailed picture in the but then, quartz is something you can solve. You can shape. Making out ends that can be easily plugged for gas tank sealing solder. So depending on the temperature, you can create this controlled atmosphere inside a quartz tube or inside the ceramic. That's very long. And then you'll be basically turning the CO2 knob. You can turn the temperature knob as well, because CO2 and temperature will go in sync. So you can see on the element diagram, you can choose different temperature and you will get different answers. So if you're doing it 800, you'll be going through this intersecting form that will give a different values. And if you go to high temperature, so those are two knobs. Typically, you could fix the temperature depending on what furnace you're using. And obviously, the higher the temperature, the kinetics will be faster. So you want to go to the highest possible temperature and then turn the CO2 knob. That's much easier because the CO2 knob can be controlled by mixing ratios, which you can change. So this is the type of experiment people do in this controlled atmosphere concentration plastic. And going to like the ceramics community used on a daily basis. So students who are working on some sort of electronic ceramics that interior, they're always creating this non-stoichiometric materials with specific level of non-stoichiometric. Okay. I don't know that any other areas of using this as widely as the electroceramics. Okay, other questions? So I give you some references I think earlier on. We have some additional references for your point defects. Particularly, I think some of those would be good for your semiconductors related point defects like surfaces and interfaces and so on. I think this one. still having semiconductor related. Some of these are. So anyway, I give you an reference you can see. So with that, I'm actually done with my defects and controlled atmosphere processing of tutorials. And see, I can start the next topic and we'll just continue with that. So the next topic will be also of interest to some of you at least, where you listen instead of DC electrical measurement, use AC electrical measurement to model the conduction behavior of the. As I said, when you use a DC electrical conductivity of your sample, direct current, then you are going to get an answer that total conductivity of your sample is such and such. If you're using two-phase material, for example, positive, or a polycrystalline material with grains and grain boundaries, then it's not going to answer then what fraction of the total conductivity is coming from phase 1 versus phase 2. Or what fraction of the conductivity is coming from conduction through the grain versus conduction across the grain bond. Because those are microstructural aspects and control that. So for example, if we take a ceramic sand and simply at different temperatures, at high temperature you will be growing the grains larger. So number of grain boundaries will go up. Or if you have a fine microstructure with smaller grain, like the ball of the grain bond. So depending on the contribution of each of the cells, it will have an impact on the overall contribution. So if you know the answer that how the grain bond is contributing compared to the grain, you can choose. You have to say, I want to maximize the number of grain components, or I want to minimize the number of grain. So that's the microstructural control. Or if you're mixing failure, and if you know the answer, that of the overall conductivity, 10% is coming from phase 1, 20% coming from phase 2, and so on. Then you know in what proportion you're going to mix, tune the proper picture. Okay, so that's the advantage. The only way you can get those answers is through AC electrical. DC will never be that answer. Okay? So what I can do now be at the basis of the physics, and then I'll do a little bit of circuit analysis because it involves circuit analysis. And I'll show you where the material scientists can come and contribute in this area the way a circuit engineer or electrical engineer will not be able to. Because to that person, it would be like, hitting the sun. Who cares what the material said? But you will see very soon that you have multiple choice to pick for your motor. And when you have multiple choice, only one of those choices is going to be correctly represented on the book. How do you know which one is to pick? So that's where you know that. Because you'll be able to process the material in the different conditions, hence change the microstructure, and help you sort out which one is the correct one. So that's where the beauty, otherwise a mathematician or a circuit engineer can always make a electrical circuit engineer. This becomes a circuit heating, which may or may not present your material at all. That's not just the very issue. Fitting wise is okay. but it's not representing what is happening through, the actual physics and chemistry that goes into stuff. So that's where I'm heading, and to give you some references if you want to read more about this. In fact, this is a good reference that I used. Number 2, it's actually a PhD thesis written by actually a Bangladeshi electrical engineer. So this is a source. There are other resources as well. So it does outline also the basics, particularly circuit analysis and the so-called complex plated blocks. And you'll see that when you're dealing with AC electrical diagram, you're actually dealing with complex quantities that will have the real part and demand. That's why we refer to as complex plating blocks. And you can see the different complex plating blocks and so. Then I'll show you that just circuit analysis and coming to a conclusion is not a joke. So often you have to confirm what you are trying to propagate or trying to conclude. You have to combine with microscopy so that you for sure you know which circuit to pick. And how does that relate to what is really happening? And finally, I'll show various applications of this technique to all kinds of electronics. Yeah? So that's the outline of the agenda, and some of the examples I'll take semiconducting or resistive touch sensors, super ionic conductor-based devices like your field cells and oxygen pumps and sensors, etc. Mixed ionic electronic material for electrode application. And this becomes very important for using a galvanic cell using solid electrolytes. Remember, typically electrolytes, we talked about advantages and disadvantages of liquid. And we talked about advantages of solid, that replace the liquid with solid layer that can conduct ionic species that we see here in liquid. Then not only you don't have to worry about containing the, but you can make two-dimensional devices, creating thin films. With liquid, because you have to find a way to contain that liquid. Okay? So, there are advantages, and we'll talk about how this impedance spectroscopy can be used to model those kind of things. And final example would be nanowire-based devices, where you make nanowires and use those nanowires to make devices. And then you can do this AC electrical measurement, sort out what's happening in those devices. Typically, you make you make nanowire. I'll talk about some of the techniques by which you can make nanowire on offset, for example. Then you can collect this by ultrasonication to shake them off. After all these are arrive, they're going to burn it, you can break them apart. You will have to clearly do very intention. So that's why ultrasonication. And you can collect those in a suspension, like water or some salt, in liquid medium. And then you can take a pipette, micropipette or some sort of pipette, and just put up on a platform. If you have a substrate with interdisciplinary electron or electrical measurement, you can pipette some of that suspension, dry it out, and fire it along, so that they will basically sitting on the top of the platform. There will be a lot of random type of arrangement and so on. You see that you can use DC electrical method to sort of model that kind of random structure. It's not very easy, but something that is doable. Okay? So that you can sort of build your ideal device. You will have to figure out a way to change the system. So there's a lot of experimental skills that you will have to involve. So with respect to a little bit of history, it was actually corrosion communities one of the very first community to use this technique of modeling corrosion heat. So some of the examples that I'll show you relates to corrosion. The electroceramics community came in late or early 19th. People who were working on ionic conductors, for example, and superconducting. This is why we this kind of measurement is like look at not only the polycrystalline material behavior, which is your next slide, but also the electrode your sample interfaces by using AC electric. So that's why they got into. And the basic idea is that you are going to represent physical and chemical phenomena that's happening in your material in terms of electrical circuit elements. The circuit elements are typically resistors and capacitors. For example, if you have a composite of two things, by doing this kind of measurement, you will be able to figure out an average resistance of phase one, an average capacitance of phase one, and same thing for phase two. That's very powerful. So that will give you fundamental property of each of the phases that is in that direction. You can get that data from single crystal measurement. When people do single crystal measurement, each of these phases, and they will give you R and C. So that's the beauty that from the body and the type of R and C you are getting, you can compare with the single crystal measurement to make sure that your circuit is correct for that. So that's one of the verification of if you are not doing it at the exact just whatever circuit completely that kind. So this is really you're picking a circuit that represents physics and chemistry that's happening in the cell. So you did with things like in B. So in DC measurement, you know that your only law will give you resistance. Where you apply static voltage, angle independent, you measure static current, angle independent. And that will give you the ratio of the two resistance. The AC equivalent of that is going to be if you're going to apply a time-dependent voltage, time-dependent on frequency shift. Yes? And so you will apply AC voltage and you're going to measure AC current. So both your voltage will be time-dependent on frequency dependent and current will be time-dependent on frequency. And you take the ratio of the so one of the usual type of voltage that you apply is so-called sinusoidal. It will have an amplitude and it will have phase length. Which is given J omega theta. Omega is the frequency and T is the time, and J is the imaginary quantity which is square root of -1. So this is what you're applying, which is the sinusoidal voltage, where the amplitude of the voltage is varying frequency. And then you are going to measure the frequency dependent current. That will be phase shift. So this was J omega T, it's now J omega T plus there is a subtract height. Do you know what that theta comes from? Where the theta comes from? So you're applying a voltage, and the current will be shifted on that plot by that amount rate, angle rate. And so the current will shift and use a similar pattern, but the current will be shifted with respect to voltage. And that actually represents the dielectric leap or delay, in the sense that as soon as you apply voltage, current picks up to a certain level, but doesn't pick up to the saturation level we need. So there's a time lag. So then this is related to so-called relaxation time. People talk about that. Very important one. Right. So you can actually get relaxation time on this kind of evidence. That will give you an idea of essentially the speed of the process. So for example, let's say you took a stabilizer chromium to the oxygen and conductor, and you pick up the polycrystalline curve. So oxygen will be moving through the grain at one speed, and when it crosses the grain boundary, it will be different. And you can pick that up from relaxation time. And you will see that relaxation time will be product of R and C. And you will get the values of R and C from the electrical circuit that you will use to represent your stabilizer curve. So that's the point of where we are heading with this. Now if you take the ratio of this voltage dependent or time dependent voltage and time dependent current, you calculate a quantity called dP, not resistance setting. So the DC equivalent of impedance is or AC equivalent of resistance. And these are going to be all imaginary quantity. So you will, get a complex form, which will have the real impedance and an imaginary. And in the plotting the real part of the imaginary part, you get all kinds of things that will come. So you can use impedance analysis that will basically measure. So you, in the impedance analyzer, you put two contacts on each side, and you will apply voltage as a function of frequency. So you can start with, let's say, lower end microhertz. By the way, the larger the frequency range is, the better you will be to capture all the processes. Because all these processes will have different relaxations. So to capture all these processes, you will have to span a wide range. Combine impedance analyzer that will allow you to measure impedance from microfards to megafards. The bigger the range, the better you can capture all of this. How do you know whether you have captured it? You will see that from the AC measurement, you will get all these components, contribution from page 1, page 2, of grain, etc. And you add that up, you just add it up, resistance should be exactly equal to the DC resistance, which is the total resistance. If they match, then you know that you have captured it. If they don't, if there is a difference between measured DC and total that you get from DC, that means the frequency range you use did not pick up one of the relaxation behavior. So that's the test, whether you have captured everything. So this frequency analyzer, impedance analyzer will give you, basically you hook it up to the measurement. One column will be frequencies, microhertz, tens of hertz, kilohertz, then will go to megahertz. And then it will also split the real part of the and the imaginary part. It will give you that. to internally convert that data. It gives you data. So you have frequencies of real ingredients, imaginary ingredients. If we give you that data envelope, a fish envelope. So in the data is given to you from the previous sample. You take the data and then you start doing this equivalent to separate modeling, and you'll get the answer. We'll stop here. That's about it. We'll continue. Yeah. It's a good introduction to the, I want to clarify the physics. The rest is going to gas and circuit heating, and obvious emergence and materials. All right. No lecture today. I'm glad that I'll still go ahead and shall I go. You can tell me you can actually see all my passwords. So I'm not sure what I'm feeling. Ready to go ahead and lecture on the team file. Hopefully it was all right. I'll see you tomorrow.
Last time.